Okay, let's go ahead and get started for today. We're going to talk about distributed system structures, which is really all about networking. So I want y'all to make sure you tell me that if this whole chapter is a review, please tell me so I can make sure that next time I teach this course, I don't go over this chapter, and thereby saving future classes superfluous work. But unfortunately, you're the guinea pig, so congratulations. Any questions?
If you've already learned all this, let you know?
Yeah, if you've already learned all this, let me know.
Okay.
We've already learned.
Because I have a feeling the answer is going to be 90% yes.
Okay.
Motivations, type of networks, network topologies and structures, communication structures and protocols. Have you heard of TCP? Robustness, and I love how it says an example of networking, which in reality is just talking about networking the whole time. All right.
Definitely network topology. We got applied networking and systems analysis and design.
Yeah, we did.
All right, we have some objectives. I don't care. So motivation. What's going on is a lot of times in supercomputers, or actually in other systems as well, not everything can be done on one machine, so you need to have multiple machines. Hence the word distributed, because you want to somehow have them communicate or collectively solve a problem together. It might be, again, a supercomputer, or maybe there's some type of sharing or printing you want to do. Everyone wants to share a printer. It's a distributed system of one way or another. One thing we want to talk about, well, first off, sharing resources is very common in the workplace, sharing a printer. Supercomputers, you want to come up with some type of speed up, so that's load sharing, or even in a server room, you're going to have multiple servers, so you need to somehow speed up your computation by using multiple systems. Another actually really good feature is reliability. If you have multiple machines and you can somehow set it up that if two of them go down, you're still operating, that'll increase your reliability.
Sounds terrible.
Sounds terrible? Well, someone's got to implement it. You want to be that man? No? Okay, good. Communication. Well, hopefully you can tell that all these machines are going to need to talk to one another. And usually it's done with message passing. Although I guess you could try and do it with shared memory. But I wouldn't. All right. Is this picture confusing to anyone?
A little bit, because the network's all blobby, but it's also rectangular, so it's kind of...
Well, it's the cloud, man.
It's a very rough
So the
cloud.
server talks to the client talks to the server.
And the network's
Somehow they go
connected
through
to
the
the
network to get
resources.
resources.
Yes. Maybe the printer's over here, or network attached storage, whatever.
But why don't they go through the network to talk to one another?
Site A and Site B? Yeah, why wouldn't they do that?
Because they're both from the same place.
Actually, you know what? They should go through the network. I don't know what this line is. Maybe they have a phone line. They're talking to one another. I actually don't know what this arrow is for.
Maybe it's like Google Drive and Gmail.
That's the only confusing part on
This arrow right here that makes
Yeah.
absolutely no sense. I agree completely. Any other questions? Okay, good. So you can have network operating systems, or you can have distributed operating systems,
DOS.
which is
DOS.
not what DOS stood for at all. It was dirty operating system, and I'm not making that up. Or disk operating system is eventually what they changed it to. All right, network operating system. So users aware of different machines. You can remote login, remote desktop. This is what everyone's used to, or FTP to another one. So the operating system is part of your network of being able to communicate with other machines. Wow, lame. All right, distributed operating systems. This one is probably the new topic. You're not aware of the multiple machines. Everything operates as if you just have one machine in front of you, and whether it's talking to other machines or not is kind of hidden from you. So you may do some type of data migrations done on the back end for you. Same thing with computation migration. It may be done on the machine in front of you, or it may be done on some server as well.
And clients.
And other clients, right. Oh, thin clients, yes. So if you want to migrate a process from one machine to another, the book lists 5 things that you must look into account. One is load balancing. You want to evenly distribute the workload so that you are utilizing your machines correctly. You don't want one machine having too much work. I know, mind blown, right? You want to look at computation speed up, you want to try and actually run it multiple, if you can split up the process to run on multiple different machines, you can probably get a speed up as long as it's a long process. Very common nowadays is hardware preference. You may have hardware that's very good for any type of security computations, or maybe it's good for database access, or it may just be a good standard number cruncher, or maybe you need a certain type of a GPU hardware in order to run this program correctly. So hardware preference is becoming more and more. Actually, it was still a big thing back in the day, so it still is nowadays. Just now, you're able to see it. Back then, you'd have to have very specialized machines. But now, there's a lot more commercial off-the-shelf hardware to use, like a GPU or other hardware devices. Okay, software preference. You get hardware preference. There might be a software preference that you need to be using. And then data access. You can run the process remotely rather than transfer all the data locally. All right. Great. All right, so there's something called a local area network. I know this is new to all of y'all.
Oh, what?
LAN parties?
Yeah, LAN parties. You remember those?
I think we have WAN parties now.
Oh, I'm not with the times anymore. Oh man.
But they removed it from all the latest video games. It's lame.
It really is lame. Yeah, Blizzard is dead to me now because of that and other reasons. So it's designed to cover a small geographical area.
Like your house.
Yeah. When you use the word geographical, I'm thinking the small is like a state.
Maybe a city.
Or a city. But that's not what they mean here. They mean like your house or possibly a campus if you want to get
that's an
if you want to get
advanced network.
if you want to get pretty big, if you want to become a large, small geographical area. Anyways, multiple access, you might have buses, rings, or a star network. So I guess these slides are old because 10 to 100 megabits a second is would be pretty lame nowadays. We do at least a gigabit, sometimes 10.
They hoodwinked me.
They did?
It's taffy, it's not sweet tarts. But it's sweet tart taffy, so it's still good.
I'm glad that word hoodwink is still in use. A note is... Quiet, Chris. I did ask for your comment.
It wasn't heard over the webcam.
Oh, it picks you up.
So why is the speed isomorphic to 10 to 100 megabits?
Why is it isomorphic? Okay. Anyone want to answer that?
What is isomorphic?
Okay. Anyone want to answer that question? We're doing great. Answering questions with questions. It's your turn, Tyler.
Homomorphism.
Wait, what's just this?
Homomorphism.
Right.
Alright, I gotta go look at it first. I got a chain of looking up things.
We're going to get down to it.
Homomorphism is a structure preserving map between two algebraic structures of the same type. Okay?
We're getting a little sugar rush
So
over
is
here.
that, or just morphism. I gotta go look up that.
So are these supposed to be fast?
That
Like,
admits an inverse. So it's either 10 to 100 megabits per second or 1/10 to 100 megabits per second.
or a negative speed per second?
Yeah, so I've looked at this slide about 10
So it's
times
got
now.
really good upload speed.
Matt, I've looked at this slide about 10 times now. I have not seen the word isomorphic up here yet. So if you want to help me out here,
Just quickly.
I would
I thought
love.
that meant approximately.
Yeah.
Oh.
All right. Anyway, slow. All right, it's okay, Matt. Thank
Fast and cheap. I don't think that's very accurate either.
you. Okay. Please explain.
It's not very cheap, and that's not very fast.
Oh, no, see, an isomorphic thing is one of those squiggly lines with either a straight line or just by itself.
Mm.
Two of them together means approximately. Unfortunately, the symbol is also used to denote geometric congruence.
So this is not a math class, so using the word isomorphic is probably not going to come up too often. Could be wrong.
I'm in the wrong computer class for that.
Okay. So it is fast and cheap relatively to wide area networks that are going to come up. A node is usually a workstation or a personal computer. And sometimes you'll have one or two of these mainframes. When was the last time y'all seen a mainframe?
Never. Dexter's Lab, actually. 1997.
Isn't that what personal computers are now?
No. A mainframe is usually more of a machine that multiple people log into. So it'd be more like a server. Those are just switches. There's no server up there.
Okay,
Depiction of a typical LAN. You have your app server with your workstations connected to a gateway with a printer, laptop, and a file server. Wow. I don't know if I'm okay with this picture. Nah, that's fine.
I mean, it works.
Yeah, this picture works.
So who's the gatekeeper?
And who's the keymaster?
That one.
So a wide area network, which is the opposite of a local area network. The hint is, of course, that
The
local.
opposite of it?
It's local and wide. I don't know how that came about, but anyways, links geographically separated sites.
Whoa, geographically separated.
Yeah, so like the road.
Oh.
Point-to-point connections over long haul lines. I like that term. Often leased from a phone company. I like how it says its speed is 1.5 to 45 megabits. All right.
Megabits.
Megbits. Oh wow, yeah.
What unit is this?
What unit is a megabit?
Schmemgit?
Oh, did we not talk about broadcast? Oh wow, broadcast. All right, we'll get to broadcast in one moment. Usually a high percentage of mainframes, aka servers. All right, so broadcast. Did y'all do broadcast in applied networking?
Maybe.
What was broadcast?
Refresh
One
us.
message to everybody.
Yep.
Why is it cheap on a LAN?
Because they're on a bus, it goes down the bus and just drops it off.
Simultaneously, essentially. Why is it? Well, it's actually a poor choice and usually blocked on a LAN.
Because it's got to deliver it to a server who then has to translate it and resend it out.
Yep. Terrible hardware support. I didn't even look at this picture before I.
Getting into chemistry.
Yeah.
Those look like chemistry.
The hydrogen is
So you got
bonded.
your H atom up here, or molecule, which has user processes of a host operating system. All right, that's cool. And then you have your communication subsystem. Okay, so you have your two host networks. There might be some internal wide area network in the middle containing a lot of different communication processors that they then communicate to other ones. All right. The protocol is how they communicate. The processor is the physical hardware. Come on, man.
Why isn't there a line between the left and the right processor like there is between the top and the bottom processor?
I don't know what you're talking about.
Oh, I
Come
know
up here and point.
exactly what he's talking about. There's no
It's
line
like a
in the
half
middle.
mesh.
Oh, you mean from here to here?
Yeah.
Yeah.
It's not
Now
a
all our
complete mesh.
nodes
Oh.
are connected.
Probably because they're geographically speaking, trying to go from here to here is too much of a distance. And the phone company didn't want to lay a line.
That's the real answer.
Oh yeah, the second answer. The phone company didn't want to lay a line. How often have you gotten the cable company or the phone company to lay a line for you?
When you pay them money, they'll do it.
Yeah. Right, without paying money.
Oh, if you're not paying money, they're not doing crap. You better already be there.
That's what I thought. All right. Network topologies. Did you know there's different network topologies?
Sure.
So they have to be physically connected some way. So you have to look at installation costs, communication costs, reliability, and also how fast they are. All right. Do we get to see pictures of them? Oh,
Yay.
all right.
Oh, yeah.
So have you seen this before?
Yeah. I think it was in the architecture book, too.
Oh.
Because I vaguely remember looking at the book and seeing these shapes.
All right. Which one's the fastest?
The mesh.
I don't have the word mesh up here, actually.
Fully connected
First
network.
one, yeah.
Thank you, Chris. All right. Which one's the slowest?
That depends.
Great answer. That was a great answer.
But the fully connected network is always one of the fastest.
You're-
It may
if not,
be in a set of the
it is.
fastest. Communicating F to E in this case, the ring might be just as fast.
Which is the most expensive?
The fully connected network.
Which one's the worst though?
It depends.
Is there one that
I
just
trained you
flat
so
out
well.
the worst?
No, it depends.
Going
So
from
if-
C to F is really horrible in the tree structured network.
So if a lot of people, if a lot of
But
people,
going from C to F in the, what, okay, so, but going from C to B is really quick.
so the star one would be good if a lot of people had to go to C and not much else.
But
Right.
C to B is
Cool.
horrible in the partially connected network.
Well, the problem with the star network is your C's can get overloaded, right?
But
Mhm.
arguably, the ring network is just the worst.
Usually well,
Because data flows in only one direction. You gotta go
two
that-
directions, right?
No.
It depends on your ring. That's true.
Well, I mean, they just said that, the other books just said it always flows in one direction.
Oh, okay. We can do that.
So benzene is the worst.
Mm-hmm.
So depending on which way it's flowing, either F to A or F to E is always really slow, even though they're connected.
All right, sounds good. Any other questions?
No.
So the design of a communication network, right, must address four basic issues. All right. Namely, how do you name them? Namely, how do you name them? Oh, wow. How do you locate one another? How do you route it? How do you send a sequence of message and contention? So figure out where it's going. How do you route it there? In general, you're going to have to, at some point, part 3, break up your message. So you have to, how are you going to make sure that you can complete your message? And then contention, you're always sharing a resource. So what happens if the demand is too high at some point? What if someone is using it? What can you do?
FDMA.
FDMA. All right, naming. We usually do something with either IP addresses or domain name service. Y'all good with that?
Sure.
Yeah.
You sure, Chris? You look like you were about ready to say something.
C all in at 192.168.200.12. Got it.
Routing strategy. You could fixed route everything. So A could go to B, B could go to C like a ring, and it would always be that way. Since you usually choose the shortest path, your communication costs can be minimized. Unfortunately, load changes are meaningless to you, so you might get a bottleneck. It also ensures messages will be delivered in the order they're sent because they're always flowing in one direction. You can't take two paths and one getting there before the other. So fixed routing has some nice capabilities, but it's terrible with load balancing, which actually makes it a horrible solution a lot of times, but not always. Virtual circuit, I don't even know why we talk about it anymore, but you basically have different paths. And I think virtual circuit makes more sense when you talk about dynamic routing. Or is that packet switching? Oh, well, dynamic routing. The path is chosen when the message is sent. So it wants to send a message to A, then it finds the path and sends it along. Virtual circuit, you've set up a session first, and then that's your routing as well. So hopefully you can see that these three are going from very stringent to not stringent at all. The issue with especially dynamic is that the message may arrive out of order. What's great is that if there's a load change, you can adapt to it very quickly. So usually messages arriving out of order, you have some type of sequence number to each message. Are y'all used to seeing that as well? Which protocol had that?
TCP/IP.
Just TCP. IP is routing. But yes, you are correct. All right, connection strategies. So circuit switching. It's like a telephone. Your system. Message switching was a temporary link for the duration of one message. Okay, right. It's like your session in a way. And then packet. Every time you send a packet, it may take a different path, and then has to be reassembled when it arrives. Which of these three do you think is commonly used?
Packet packet switch.
Packet switching.
Yeah, packet switching. All right.
Sysma.
Does this look familiar?
Sysma doesn't.
Okay.
But let's read what it is before we get to that.
Okay.
Yeah, that does sound familiar, but not the name.
This book uses different names sometimes.
That could be it.
Basically, try and just determine if you can send it. If not, either wait or route it somewhere else. Contention. So originally we did token passing. A unique message known as a token keeps going through the whole system, like in a ring. And whoever has the token is the one that can talk. So you can't do anything until you get the token.
So like Chuck E. Cheese's.
Right. You got it. That was a great analogy that you pulled out of nowhere. By the way, I couldn't believe how much my kids love Chuck E. Cheese. It's amazing.
They've really gone down in quality though. They got rid of the animatronics.
Wow. Well,
Like
when I
the
did
classic ones.
when I went as a kid, it was a bear.
The creepy bear.
Yeah, I love the creepy bear.
I mean, everyone loves
They
it.
need to bring back Discovery Zone.
Yeah, they do.
Oh,
That place
yeah.
was the best.
Yeah.
They had those all over the place, or just because there was one here.
I grew up in San Antonio. They were.
They have one?
Oh yeah.
I love that place.
And the bear one, I can't remember what the bear was called anymore, because the word Chuck E. Cheese was just stuck in my brain. All right, what were we talking about? All right, token passing. Message slots. You have fixed link message slots that can circulate throughout the system. Yeah, so this is more of the ring structure. Again, with the ring structure, actually. The token can be with the ring structure, but message slots so you could communicate during certain paths. And then, oh, it's not going to do anything else. Okay, great.
Sweet.
Okay, let me pause here.